So I see that it's much cooler in here today. That's a good thing. So there are some fundamental theorems of Waldhausen K-theory. And all of these theorems need something called a cylinder functor. And in chain complexes, it's the cone of a mapping from A to B. But in general, if you have a map like this, the cylinder of F, let me write cylinder, is so how should I think about this? One of those C words. Okay, so if I have a map topologically from A to B, then this is the cylinder that I have in mind. And it's a cylinder, not a cone. And the cylinder in chain complexes is AN plus AN minus 1 plus BN, and then A. See, I'm doing this, I hope I'm doing this right, N minus 1 plus AN minus 2 plus BN minus 1, so that my differentials are going down. So here's your differential, here's your differential, here's your differential, and then this map is F. And now the catch is that there's signs on here, so I'm just going to put plus or minus on all of these, because trying to worry about the signs is a time-consuming thing. So this is the cylinder in some sort of category of chain complexes, and this is the cylinder in topology. And the basic principle that you have of the cylinder is that you have a cofibration from here to here, you have a projection from here to here, and this is the evident map. Namely, it's F on the first component and it's the identity on B. So all of these are using the fact that you have a mapping cylinder. And they also use that the weak equivalences in your category. Let me think. I'm using C. And the condition is that if you have a pair of composable maps, and if that gives you 3 different maps, if 2 of them are weak equivalences, then so is the third. Now, some of this is obvious from the fact that it's closed under composition, but the thing that's not obvious is that if the composition is a weak equivalence and one of the others is a weak equivalence, then so is the third. So this condition is used a lot. Okay, so the first one is additivity. And it has lots of equivalent formulations. So if I look at the category of short exact sequences, and I want to remind you that this is the same thing as S2 of C, that you have functors. So let's say a C contains 2 categories, A and B. And then you look at all sequences of A to something to B. So these are short exact sequences in your ambient category C, where the first fellow is in this subcategory and the second fellow is in this subcategory. And then, so then you want to say that the K-theory of E is the same thing as the K-theory of A cross the K-theory of B. Now, I'm not going to prove this because I have 2 hours worth of material to do in this 1-hour lecture without the proofs. So if you want to see a proof of this, you can look in the literature or in my K book, so I should probably just say K book, AMS 2013. And I think that there are a few copies of it floating around in the audience anyway, so the proofs are there. Okay, so the
what is A and B?
So one thing that you can do is, A and B are two Waldhausen subcategories of C. So let me give you an example of how this works.
Subcategory.
Oh, dyslexia, yes. So suppose that E is this category, and so inside of here I have A sitting inside of here is the sequences which are A to 0, and you also have B sitting inside of here is the sequences 0 to B, and so here you have a Waldhausen functor, and here you have a Waldhausen functor. This Waldhausen functor gives you a map from the K-theory of A to the K-theory of E. This Waldhausen functor gives you a map from the K-theory of B to the K-theory of E. And so then you have a natural map like this, and the assertion is that that's an exact sequence. So here's an example. So suppose I look at chain complexes, and so I want to look at chain complexes which are exact. And so if n equals to 2, I'm in this particular case up here. So then I want to look at A is the set of all things of the form A0 to 0 to 0. And B is the set of all things which are 0 to A1 to AN. Then E, this category, has got two subcategories, A and B, and the extensions of something in this category and something in this category would be everything. So what this says is that the K-theory of, I didn't name it, A from 0 to N, exact, is the K-theory of A, cross the K-theory of A from 1 to N, exact. And then by induction, it is the product from, let's see if I can get my indices right, see if I can find it. I'm not going to find it. So let's just think, if I did 0 to 1 to 2, that would be this case, so it's got to be 1 to n of copies of K-theory of A. Okay, so another application of this is additivity. If you have a bunch of additive, another application is that if you have a short exact sequence, 0 goes to F1, goes to F2, goes to F3, goes to 0 of functors from A to somewhere else. Let's call it D, just to have a name that doesn't conflict with anything. Then you have a category. Let's see, so here's A, here's E, and here's B. And so the map here sends an object A to the extension F1 of A, whoop, yeah, all right, A to F2 of A to F3 of A. And then here you add, and you get the K-theory of B, whoops. And so this theorem tells you that F1 lower star plus F3 lower star is equal to F2 lower star as functors from the K-theory of A to the K-theory of D. Okay, so that's the the first of the fundamental theorems. And depending on how you look at it, it's completely obvious and completely mysterious. The second one is localization, which has a lot of different names, but this is a name that I'm choosing. And so if you have a Waldhausen category and you have two notions of weak equivalence which are compatible with the cofibrations, and one is the V weak equivalence and one is the W weak equivalence, then you write C upper W is the subcategory of all objects, the full subcategory of all objects which are weak equivalents to 0. And then you have the K-theory of CW goes to the K-theory of C. Oh, well, let's see, I didn't say that, but you have to use a weak equivalence. So the weak equivalence you use here is V. Then you have the K-theory of C with this particular weak equivalence. And here you have the K-theory of C with the final equivalence. And before telling you what that's useful for, I'm going to give you the third one. And it's the approximation principle. And what it says is that if A to B satisfies, so here's F, then the K-theory of A is equal to the K-theory of B. So I have to tell you what app is. And so if you're given A and a map from F of A to an object in B, so I'm not going to write out in all words what this is, so I'm just going to write it symbolically. For every map from something in A to something in B, there exists a map in A from A to A prime, such that if you apply this, and there exists a map like that, and that's a weak equivalence. Okay, so this is the approximation property, and let me give you an example. Yes?
So I don't understand the statement in the localization property.
Yes.
What is the statement?
O is a vibration sequence.
And can you give an example?
Yes, I will. But I wanted to state this property first before I gave this application. So that if you think about stably free modules, which are projective modules, such that when you add a free module to them, you get a free module, a finally generated free module to them. Then, and then A is a category of free modules. Then the approximation principle applies to the category of free modules inside of the category of stably free modules. And what that says is that the two categories have the same K-theory. So, so for example, if I want to look at the K-theory of all projective modules.
Sorry, can you repeat what app was?
App is this condition. If you're given a map from F of A to an object A of the first category and an object B of the second category, and a map from F of A to B, for all of these, there exists a map in A like this, and there exists a weak equivalence in B like this, such that this diagram commutes. Okay? I have an example up on the board here of these exact sequences, and I'm going to use that. So let's say C is the category of bounded chain complexes of things inside of some category like projective modules or R modules or something like that. And I take V to be isomorphism, and W to be quasi-isomorphism. In other words, an iso on homology. So what we get is a fibration sequence, but now let's just think about what is CW. CW is the subcategory of all bounded chain complexes with the property that they're quasi-isomorphic to zero. So this is all exact chain complexes. And if I take C with with V, so that is all chain complexes which are and then you're just looking at isomorphisms. Then the K-theory of this is the same thing as the product of copies of the K-theory of C. Well, let's see, direct sum. Basically, for you, you can just forget the differentials. So, suppose that I look at chain complexes. So the notation that I was using up here is that the subscripts are telling you from where to where I'm going. And then I was using the word exact. So here's the K-theory of chain complexes, which are between degrees A and B. And then here is the K-theory of A, where you just take the Euler characteristic.
Can you tell us which equivalence?
So this is quasi-isomorphism, and this is quasi-isomorphism. Yeah.
Is your example about saying that the K-theory of CW, then you get the copies of K-theory of A?
Yes. What I'm saying is, so let's just say that this is from 0 to n, just so that I can index things. This example up here says that this is the product from 1 to n of the copies of K-theory of A. I'm sorry, what?
KCV equal to sum of KC.
Where are you? Are you up here or there?
Now I'm there.
Here?
Yeah.
W.
Ah, so let's just write this. Chain complexes from A to B on the category A relative to the isomorph. Let me write iso here, just so that we're clear. So this is a direct sum from I equals A to I equals B of the K-theory of A. Is that what you're asking?
Yep.
Okay. The point is that I know what this is. No, the point is that I know what I'm trying to do, and I know that I don't have time to do it, and so I'm trying to think of a way to make this presentation be comprehensible.
Sorry, you're doing an example for the localization.
So the point is that I'm trying to compute the K-theory of this category of chain complexes which go between index A and index B. And I know what this is, that this is a bunch of copies of the K-theory of A. And all right, so I'm sort of stuck here because I'm seeing too many blackboards. We have chain complexes all over the place. We have chain complexes. Let's think in terms of this diagram. We have chain complexes which are going from 0 to n, and the quasi-isomorphism that we have here is this is quasi-isomorphism. And here we have chain complexes which are exact and going from 0 to n. And here what we have is the K-theory of all of the chain complexes.
Chuck, don't you have isomorphism in the window? V is
Which one is, which one is V and which one is W? That's what I'm not.
the smaller one. Yeah, so V is isomorphism.
V, that's what my problem is. Okay, so this is, does that make sense now? Have I finally been able to apply this statement to this application? Okay, so this is from 0 to n, K-theory of A, and so therefore this is the same thing as the K-theory of A. Well, so now the point is that you take the direct limit, which is the direct co-limit actually, as A goes to minus infinity and B goes to plus infinity. And so one of the fundamental properties of K-theory is that it's going to commute with filtered co-limits. So this is a filtered co-limit, and when you do that, what you end up with is the K-theory of the bounded chain complexes on A. So this is the co-limit of the K-theory of the chain complexes which are going from A and B on A, which is the co-limit of a bunch of things which are homotopy equivalent to the K-theory of A, but all of these are the same, and so you get the K-theory of A. So this is the theorem I stated last time. So the theorem says, and it's due to Waldhausen, but he didn't actually phrase it this way, and so the formulation that is more or less this way is Gillet, but the actual formulation I'm using is due to Thomason. And that says that the K-theory of the chain complexes bounded of A with respect to quasi-isomorphisms is the same thing as the K-theory of A. So in order to prove this theorem, what I used was the localization sequence, but I also had to use the approximation sequence. So this is sort of giving you an idea of how these two things combine. Okay.
It's actually a diploma thesis. Students bring German.
In what decade? Okay, so put the last thing up so that everybody can read it. That was the request that we had yesterday, yeah? So here's what?
The category C, H, and E have cylinder.
They have what?
Cylinder.
Yes, it does. You have to be careful about how you actually apply it, but yes, it does.
Yeah.
So the main application suppose you have a ring R, a strictly perfect complex, is equal to a bounded complex of projective modules. So that's the category of projective modules. So that's what a strictly perfect complex is. And a perfect complex is one which is quasi-isomorphic to a strictly perfect one. So that's the same thing as isomorphic to 1 in the derived category of the ring R.
So you are zigzag of quasi-isomorphic.
I'm sorry?
Zigzag of quasi-isomorphic.
Well, I didn't say anything about the weak equivalence here. But the point is, quasi-isomorphic is the thing that you're modding out by to get the derived category. So for example, if you have, if your ring R is a polynomial ring over the field, and then the chain complex would be 0 to F to 0, where X is equal to 0. So this is a module over the ring R. This is an example of something which is perfect, because it's quasi-isomorphic to the complex, which is 0 to R, or multiplication by R to 0. Okay? So that's an example of something that's perfect, but not strictly perfect.
My question was, quasi-isomorphism is stronger than the isomorphism in your particular picture, because it means zigzag of the quasi-isomorphism.
I'm not saying that the morphism is from one complex to another. You can go by a zigzag. And so, yes, you're right. I'm being a little bit sloppy about what the word quasi-isomorphism means. So, but if I look at the chain complexes which are bounded inside of here, and I map, and I take anything which is a chain complex which is homologically in this direction, then I can always resolve it, do it using a Cartan-Eilenberg resolution, for example, and replace it by a complex of projectives. And therefore, any zigzag of quasi-isomorphisms, if I lift it to that projective, can be actually moved into a map of the complexes from P to there. So if you have a quasi-isomorphism from this complex to this complex, and you replace it by this P, then it's always this kind of a zigzag. So they're both quasi-isomorphic to this perfect complex, strictly perfect complex. So the point is that the approximation principle applies to this, because if you take anything which is bounded below, you can take a projective resolution. But also, if you take any bounded complex of things, or even any homologically bounded complex of things, you can do a good truncation to kill all of the things which are in this direction. And that makes it quasi-isomorphic to something which is homologically in the minus sign, so the approximation principle applies to this as well. And so the point of this is that also the K-theory of perfect modules is the same thing as the K-theory of the strictly perfect R modules. And that's the same thing as the K-theory of R. Okay? Yeah, you have a question first and then you. Okay, what's your question?
So like CHDT, really mean bounded complexes?
Strictly bounded chain complexes where every object is a projective module of finitely generated projective.
But by CH perf, you don't mean like negative degree complexes of perf.
So the minus sign just means that it's eventually zero in that direction.
These are perfect complexes, or they're complexes of perfect complexes? Because perf denotes a category of perfect complexes. I mean,
Okay. No, you're right. The notation's redundant.
okay.
But my idea was that being redundant would make it clearer. And apparently that didn't work. It backfired on me. So what I mean here are the chain complexes, which is eventually zero, and are quasi-isomorphic to a bounded chain complex of projective modules. Okay? And these are the ones where I just dropped the condition that they're eventually zero, but since they're quasi-isomorphic to something which is bounded, that means that the sequence is exact, eventually out, and I can just truncate. Now, there's no reason why I did the ring R. Well, there is a reason why I did the ring R, but you can talk about strictly perfect. So now I'm going to I'm trying to make him happy. So this is bounded chain complexes where the objects are algebraic vector bundles or locally free modules of finite rank. And the approximation principle applies. And so what you get is that the K-theory of perfect things is the same thing as the K-theory of strictly perfect things, which is the K-theory of the varieties. So what you get is the K-theory of perfect things on X is the same thing as the K-theory of strictly perfect on X. It's the same thing as the K-theory of X. Okay, and this particular theorem that says that things which are just bounded chain complex, let's take K-theory of X. These are just vector bundles, locally free modules of finite rank. And you're looking at the K-theory of that Waldhausen category. There's no cylinder functor. But as soon as you move over here, you have a cylinder functor. And as soon as you move over here, you have all kinds of ability to use the fundamental theorems, which you can probably still see if you've got X-ray vision. They're still on this board. So over here, you have all of the power of the theorems of Waldhausen K-theory. And so what has happened since Thomas and Trobau's paper was written 20 years ago is that people have stopped looking at this viewpoint and have started looking at this viewpoint. And so looking at the K-theory of perfect modules is, but this was presaged. By Grothendieck a long time ago. And the point is that this is different if X is not quasi-projective or smooth. So I don't want to go into the technical details of this, but The point is that Grothendieck recognized back in the 1960s that this was already an issue, yes.
So the kx on the right-hand side is defined as the Waldhausen K-theory of vector quantity.
That's right.
Not the definition of
So by this, what I mean is the naive K-theory. So this is the K-theory of vector bundles on X. Yes. So if you're not in some sort of a nice geometric setting like a quasi-projective variety. So a quasi-projective variety is just a variety that is embedded into some projective space, either as a closed subvariety or an open subvariety or an open subvariety of a closed subvariety. And so those are the situations that people look at in algebraic geometry. And if you're not in that setting and you have a scheme which is technically a scheme in the sense that the definition works, but isn't geometric in the sense that it's not quasi-projective or smooth, then really strange pathological things can happen. So we try to stay away from that whenever we can, because there are beasts under your bed that will bite.
Chuck?
Yeah.
I remember there's also the condition of X quasi-compact, quasi-separated and emitting an ample family of line bundle. Is this the same condition, or is this slightly more general?
Okay, so smooth is essentially the same thing as what you just said. So if it contains a subvariety which is quasi-compact, and outside of that subvariety which is quasi-compact, then it's smooth, but not necessarily quasi-compact, then it has an ample family of line bundles. So yes, you're right. There's a little bit more generality to be squeezed out of this. But I only have 4 lectures. And so I'm just not going to think about that at all, because it's painful. Okay. So let's see where we are here. I've used up way more of my time than I thought I was going to use up. Okay. So here's an application. Suppose that S is a multiplicatively closed set in a ring R. And if you move over to algebraic geometry and you let X be spec of R, then S inverse of R is going to sort of correspond, if S is finally generated multiplicatively closed set, it's going to correspond to an open. So if you have something like that, then you can look at the G theory of R. Remember, this is the K theory of finitely generated R modules. This is the same thing as the K theory of bounded complexes of R modules. Why is that? That's because the category that I have right here, that's an additive, well, in fact, that's an abelian category, at least if I assume the ring is Noetherian. And so what I did before with the bounded chain complexes applies exactly to the setting. It happens to be not only a Waldhausen category, but an exact category, not only an exact category, but an abelian category. So I can think about the K theory of finitely generated modules as the K theory of bounded chain complexes of finitely generated modules. Okay, so now I have a functor from the K theory of bounded chain complexes of S inverse of R modules. But I also have the K theory of bounded chain complexes of R modules. Well, let me just write R relative to the condition W, where W is, so if I have a chain complex and I have a map in R modules. This is in W. If S inverse of C to S inverse of C prime is a quasi-isomorphism in modules over the inverse ring. So here I have a Waldhausen category. I have bounded chain complexes of R modules together with this funky notion of weak equivalence. And the point is that if I take any finitely generated S inverse of R module, then I can take a list of generators and I can find a finitely generated R module inside of it such that its localization is equal to the entire thing. And that means that the approximation principle applies to say that the K-theory of these two things is exactly the same. So, now what is the K-theory of chain complexes of R modules relative to this funky notion which I'm calling W? These are chain complexes of R modules. Let's call it C, with the condition that S inverse of C is exact. S inverse C is quasi-isomorphic to 0 when I go up to here, means that S inverse of C is an exact complex. So the definition is the K-theory of R on S is the K-theory of this complex. Complexes of R modules which are S inverse of C is exact. And the theorem that I've just shown you here, the localization theorem, says that the K-theory of this to the K-theory of this to the K-theory of this is a fibration, says that the K-theory of R on S to the K-theory of R to the K-theory of S inverse of R is a fibration and sequence. And that means that you get a long exact sequence on groups. So here's Kn plus 1 of S inverse of R, and then the boundary map to Kn of R on S to Kn of R to Kn of S. Here's your boundary map, and so on. Now, what was the question? Excuse me, this is S inverse of R.
You mean G theory here?
Sorry?
You mean G theory here?
I do. So the point is that I had hoped to say the same thing with K-theory by now. And I didn't get there. So let's just say that the same argument applies. To the K-theory of X on Z, to the K-theory of X, to the K-theory of U, where Z is X minus U. Excuse me, your point is well taken. I know you're going to say it. These should have been G's. Exactly the same argument applies in algebraic geometry. The difference is that you have to be a little bit careful. If you have a coherent module on U, then locally you find a list of generators. But since I'm dealing with quasi-compact things, then I can find a list of generators which will work globally. So therefore, every coherent module here comes from a coherent module there, and I don't have to think. I'm assuming R is commutative. Yes, I apologize. If you don't assume that R is commutative, then you have to assume something about S, like that it's central or that it satisfies an order condition. But yeah, the point is that I want to move on. So, since I want to move on, I'm going to just make an assertion. And then that assertion is not going to be proven by me today. So there's a key lemma. That says that let's C dot be a complex, strictly perfect, complex on U such that the class of C dot in K0 of U is in the image of K0 of X to K0 of U. Then there exists a strictly perfect complex on X, let's call it C tilde, such that C tilde restricted to U is quasi-isomorphic to the original complex C. And so this is basically the condition app. And what it allows me to do is to replace G by K. So what you have to do here is instead of looking at all complexes of perfect modules on U, then you have to look at complexes on U which satisfy this condition that their class in K0 is in the image. And the point of that, yes, I'm going to do that, but my hands are full, so. Okay, so the point of this is that when I say fibration, like you think fibration of topological spaces or fibration of spectra. And if I say fibration of topological spaces, then the long exact sequence you get from a fibration just goes pi 0, pi 0, pi 0. But if I'm looking at a fibration of spectra, then it goes pi 0, pi 0, pi 0, pi minus 1, pi minus 1, pi minus 1. And so I have to worry about whether or not this map is onto on pi 0. Well, what does it mean to be onto on pi 0? That means K0 of this has to map onto K0 of this thing. And that's why you have to do this. And the whole point there is that when you think about spectra, you run into this problem that on pi 0, things are not exactly going to be onto all the time. And so you have to make a modification for that. And that's where negative K-theory comes in. And that's what I'm going to do in the next 10 minutes if I'm lucky.
Sorry.
Yes?
I'm confused about your assumptions on K, like K, R, and S.
Yeah.
Your modules are projective,
K means projective modules,
but the R and S.
and this is chain complexes of projective R modules that when you localize, they're exact. Okay?
And K of X on Z, is there anything I should know?
So these are chain complexes. So projective gets replaced by vector bundles, right? So they're chain complexes of vector bundles with a property that when you restrict them to the open subset U, they're exact. Okay. So the negative aspect of these sequences is that this first term is very hard to figure out in practice. So if you're trying to understand the K-theory of R and you understand the K-theory of S inverse of R, for example, you're stuck trying to understand what this is. And that's not an easy problem. And there are some results in the literature about it, but it's really not something that we understand very well. Okay. So, negative K-theory. Of A, and I'm not going to specify what A is. But A could be projective R modules, for example, or it could be just finally generated R modules, or it could be lots of other things. So, what you want to do is you want to extend the spectrum, the Waldhausen spectrum, K of A, to a non-connective spectrum. So I will write a B up here just to have a name for it, so that so pi n of K of A to pi n of KB of A. So this is the same thing as Kn of A. Is an isomorphism if n is greater than or equal to 0. And if n is negative, K of A is equal to 0 by construction. But what does a spectrum look like? So a spectrum here means a sequence of things, E0, E1, E2, and so on. And when you, so this is called, this is spectrum E. I want pi n of E to be the direct limit as k goes to infinity of pi n plus k of ek. So you might have a topological space. So here's an example. And I want to remind you that Ku means Z cross Bu. So Ku loops on Ku, Ku loops on Ku, etc. So it's alternating between the K-theory of U and the loops on the K-theory of U. And the point is that the loops on K-theory of U is the same thing as the K-theory of U. So, I mean, I'm saying K-theory of U, but it's the K-theory of unitary bundles. So this is a spectrum. And for example, pi minus 2 of this spectrum, so let's call the spectrum Ku. Is the limit of pi minus 2 of Ku goes to pi minus 1 of loops KU, goes to pi 0 of KU, goes to pi 1 of loops on KU. Well, that's 0, and that's 0, but this is Z, and this is Z, and these are all isomorphisms from this point on. So you get a negative homotopy group coming from the fact that although originally you couldn't have had anything in negative homotopy groups on a topological space, by the time you get out far enough, then you can talking about real homotopy groups in the sense of classical topology. So in fact, what happens here is the pi n of KU is Z, or 0 with n even, integer, and odd. So this is the difference between a connective spectrum, which are the things that Waldhausen constructed using the SS to the WS to the N, and the negative groups. So the idea is to embed A in a category. Let's call it C of A with an Eilenberg swindle. So that the K-theory of the cone of A is equal to 0. So this is typically called the cone. Define the quotient category. S, well, let's see, sigma of A to be equal to the cone of A modulo A. And then you repeat this to get a spectrum which looks like K-theory of A. Oh, I say you have to prove that Kn of A is equal to Kn plus 1 of the suspension of A. And obviously this is not going to work unless n is positive. So you take this sequence of spectra, or just take the zeroth space of the spectra, and then you can define the K-theory of it as this non-connective spectrum, and then the homotopy groups of it, homotopy groups in the sense that I was just talking about here, will give you the non-connective K-theory of the ring A, or the category A, or whatever it is that we're working with. Now there's two constructions. Of the cone on A that are relevant to the talks that you're going to hear later today. And the first one is the notion of a Karoubi filtration. So you have, I'll just use E for whatever this is, and then every object E of E has a filtered poset of decompositions. So E is equal to E alpha direct sum A alpha, where A alpha is in my category A. And the condition is that every map from an object A to E factors. So for every map like this, there's an A alpha, and there's inclusion and there's a map like that. Now there's a dual condition that every map from an object of E to an object of A factors in a similar way, but that's not necessary in reality. In the second condition, so what you can do with the second condition is, well, let me think about this. I'm going to just go with this. So this is the formal closure of A under countable colimits. So so if I look at contravariant functors from A to abelian groups, so these are usually called presheaves of abelian groups, then this category of presheaves has arbitrary direct sums, arbitrary push-outs, arbitrary colimits of every single kind. And so in this particular category, you can look at everything which is a countable colimit of objects in A. And then by the construction, this condition is satisfied. And so I only have to tell you what the Eilenberg swindle is, and that is, what is my object A infinity? Well, it's A plus A plus A plus A. It's the example I gave you the other day when we were in the question period. So this object is a direct limit of objects of A, because if I take any finite limit of finite sum, that's in A. But the infinite sum may not be. For example, if I'm looking at finitely generated modules, the finite sum of these is finitely generated, but the infinite sum of them is not. So the point of this is, this category satisfies the condition that you want. It's closed under countable colimits, so that I have this Eilenberg swindle going for me. So I have embedded it in a category with an Eilenberg swindle. The Eilenberg swindle implies that this is the case. And then, because I have this fibration sequence, which goes from the K-theory of A to the K-theory of the cone of A to the K-theory of the suspension of A, then I have this long exact sequence, except for the following problem. I have to be a little careful there. And the reason I have to be careful is because on pi 0 to pi 0 to pi 0, what I really want is that the pi 0 of this should be non-zero. And what I have, if I'm not careful, is that pi 0 of this will be 0, and that, this map will not be onto, and so it will not be a fibration of spectra. So I ran out of time, so I can't talk too much more about this unless you guys ask me during the question period. But the idea here is laid out, and there are a couple of technical issues that I should mention very briefly. And the first technical issue is, why does the quotient exist? And that's underneath this rug here, which you haven't spilled anything on, so that's good. But the existence of this quotient is a little bit tricky, and the idea that you have this Karoubi filtration is what allows you to do this quotient. If you work with differential graded categories, which again I was supposed to have talked about but did not, please forgive me, then you can find a direct DG category quotient, and that's the way that you would form this category here. So I think that that's probably overload, and I'm going to stop. So I'm sorry, I pushed a lot of stuff into today's lecture. It was a little bit kind of crammed in.
Questions?
So we don't want to try this sort of thing when our category A isn't, I guess, additive at least, right?
Yeah, what's A? Script A.
Yeah, so you can do the closure under countable colimits and other settings. And what I was trying to do at the very ending there was to finish by 10 o'clock, which I failed at. But that's what I was trying to do. So I was trying to simplify things. So the idea is what I laid out. And the point is that if you're in some sort of a category where you have a differential graded setting, for example, like in Morris Kurtz's talks, you're going to see that, then everything is additive and you want to look at contravariant functors to abelian groups. And the original things that Karoubi looked at with Vijayamayur back in the 1960s, that's where the Karoubi filtration comes from. There they were looking at projective modules over a ring. So there again, everything was additive. So the lion's share of all of the applications, this is good enough.
Yeah.
But if you are not in this particular setting, then what you want to do is you want to find some construction of some kind of cone with an Eilenberg swindle where you can form the quotient. And there's this little trick here is related to whether or not the category is idempotent complete. And since I'm in Europe, lots of people in Europe refer to this as a Karoubian condition. And what you really, I'm hiding the fact that what you have to do here is not only take the quotient, but you have to take the idempotent completion here. So next lecture, I'll say more about this. But if you start off with something which is not idempotent complete, then what you're going to end up with is the negative K-theory of the idempotent completion instead of the negative K-theory of the original thing that you started with, which we don't know how to define. So that's sort of like a little warning that's another thing it's under that rug. Yeah.
So is the point of this last construction to build a spectrum and give us stable point of view?
I'm sorry?
Like, we're starting with a spectrum?
You're starting with a spectrum, and what you want to do is you want to generate negative groups. So for example,
does that mean the same thing as finding another spectrum that has, so that this one, there is like the other two groups of this spectrum are stable original spectrum?
what you want to do is you want to take the sequence that you had, which is this part, and you want to continue it. And the reason you want to continue, well, there's several reasons why you want to continue it, but the major reason nowadays why you want to continue it is because there's this thing called Zariski descent. And if you want any kind of cohomological descent condition to be true, then what you have to have is negative homotopy groups. And it just comes out of what you need in order to have descent, that you need the negative homotopy groups. So that's maybe the modern way of thinking of it.
This could be done with any spectrum. Is that true?
If you give me an arbitrary spectrum, then I have to decide what I'm going to do for my cone. And a different choice of a cone might give you a different de-looping. So for example, you could have two negative spectra, well, let's be stupid. You could have a negative spectra which has no homotopy groups in positive degrees. So the connective version of it is 0. But it's got lots of negative homotopy groups. Now, how would you generate something like that if you just started with 0? I mean, out of nothing, you get nothing. So if I look at this topological K-theory example, for example, and I truncated it so I'm only looking at the negative homotopy groups of it, that would get such an example. So if I look at KU, there's this connective version of it. And this doesn't really have a name, but this is the thing which has all negative homotopy groups, all Z's in negative even groups, but 0 everywhere else. In particular, all the positive groups are 0. So if I did the connective cover of this, I'd get nothing.
I think the error was the other way. So it's cover.
I have to think about that. You may be right. Yeah, the arrow does go the other way. Thanks. So I'll slow down more in the next talk. But I had to get in a certain amount of things that were sort of like requests by the other speakers. So I'm sorry about pushing on this lecture.
Okay. I think that's it for me.